In this worked example, we're taking a look at the physics of spectra. This is for astronomy. The question reads, a beam of light consists of a continuous range of wavelengths from 420 nanometers to 740 nanometers. Students of physics should recognize that as optical wavelengths, right? So this is from like purple light to red light. The light passes through a cloud of cool gas, as shown in figure 11.1. So we have the incident light, they give you the wavelengths there, there's emergent light, and it says the spectrum of the light emerging from the cloud of cool gas is viewed using a diffraction grating. Explain why this spectrum contains a number of dark lines. Well, in the gas, we know that gases are made of atoms, and atoms have electrons. And so one of the first key ideas here is that the photons of light are going to interact with the electrons in the atoms. Photons of light interact with electrons in the atoms of gas. The energy in the light is going to be sort of delivered into that, into the atom, and the electrons can be either, you can think about it as excited, or they go up in energy levels. Okay. So the energy of the light excites or promotes or advances, some sort of verb that means the same thing, excites electrons to higher energy levels. The difference in the energy levels, okay, has to be equal to the energy of the photon. The energy of the photon equals the difference in the energy levels. And this is sort of a photon is a particle of light. We did another quiz earlier about how light is a particle, it's quantized, a packet of energy. And so only certain energies will work to promote electrons. There can be no in between, like definite values. So the energy of the photon has to equal the difference in the energy levels. And so as an electron sort of gets promoted to a higher energy level by a photon, that's an excited state and unstable. So the electron sort of wants to go back down to its ground state. And when it does, it's going to emit a photon with the same energy that it absorbed. But when it emits it, it could emit it in any direction. And so here on Earth, we'd see that as a dark line. It's very unlikely that the photon would be emitted in the same direction that the incident light was arriving there. So the light that emerges is going to be all of these wavelengths of light, the sort of optical part of the spectrum, all the colors of the rainbow, except for those very specific and particular values where the atom has absorbed the photon energy to promote electrons. And then again, it still emits photons back out, but it's emitting it sort of in that direction or in this direction. And so we say that the light gets scattered. Okay, the electrons scatter the photons. And so here on Earth, we don't see any of the light, that got scattered in a different direction. So as electrons go back down to the ground state, they emit photons in a random direction. Likely not toward Earth. So there are dark lines. And those dark lines in the spectrum give us a clue about the chemical constituents of this, cloud of gas. Now, this could be just a nebula in space, or this could be the atmosphere of a star, right? Like there could be light that's coming from the inside of a star that's going through sort of a cooler outer atmospheric layer, and it gives us a clue about what this star is made of, in its upper atmosphere. And so it's incredibly useful, the information that is contained in light. So 4 marks for that part of it. The question goes on to sort of give us a little figure here that we'll come back to. says some of the electron energy levels of the atoms in the cloud of gas are represented in figure 11.2. Now, you all should probably recognize these values, especially the 13.6, as some energy levels in the hydrogen atom. 13.6 was the magical value that the universe had to sort of cool enough to drop below that ambient energy to where recombination could occur, right? We studied recombination where electrons stay bound to protons for the first time. If there's more than 13.6 electron volts, there's enough energy to just promote the electron completely out of the hydrogen atom. Okay, and so they're ionized at that point. It's an electron and a proton, two ions. Beneath that energy threshold, there can be recombination, right? They can combine and form neutral hydrogen. And so we calculated that this would be like the first 380,000 years or so after the Big Bang, the universe would have had this much energy, and there just would have been the hot glowing fog that we see today as the cosmic microwave background. So we'll come back to that. It says light of wavelength 420 nanometers has a photon energy of 2.96 electron volts. Calculate the photon energy in electron volts of light of wavelength 740 nanometers. When we did this calculation before, I showed you there's two different ways to sort of think about this. One is to kind of look at the Einstein relation. So it says energy equals Planck's constant times frequency. The speed of light is wavelength times frequency. And so we can kind of see that to keep this constant, as frequency increases, wavelength goes down. So these things are inversely proportional with each other. If the energy of a photon is directly proportional to frequency, and frequency and wavelength are inversely proportional, then the energy of a photon is inversely proportional to its wavelength. In other words, the longer the wavelength of light, the lower the energy. Make this value big, this value goes low. So radio waves have the longest wavelength. They are the lowest energy form of light. Gamma photons have the shortest wavelength, and therefore they're the most energetic. We can use this proportionality because we're given wavelengths and energies to just set up a proportion and solve it. Like we're given two things and we want to compare it to this wavelength. So we should just be able to use a proportion to solve it. So that's the simpler way. If we want to solve for the energy of this wavelength light and they're inversely proportional, we just want to kind of think about how, well, the energy that corresponds with this, okay, is going to be on the sort of opposite side of the fraction. So the energy we want to solve for, the photon with this wavelength, goes up here, and so 740 would go down here. So we're comparing that 420 nanometer light to the 740 nanometer light, and we know the energy of this photon, it's given right here. So E over 2.96 electron volts is equal to this many nanometers over that many nanometers, and that's perfectly solvable. And take the ratio of those wavelengths, multiply it by 2.96, and you'll get a number. Note how the nanometers cancel. So 420 over 740 gives you 0.56 and a little bit more times 2.96 electron volts, right? So like just multiplying both sides by this, and then those will cancel. 2.96 electron volts, 2.96 electron volts, that cancels. So the E, the energy, the photon energy for this wavelength light is 1.68 electron volts, and you can solve it, just with this proportion. The other way to do it is to really sort of use these equations. Like we could plug in 740 nanometers, the speed of light, calculate the frequency, multiply it by Planck's constant, calculate the energy, but then that's going to be in joules, and then we convert the joules back into electron volts. Okay. If you want to see all of that working, just go ahead and click on the link above, and I'll show that in a separate video. For our purposes today, we just kind of want the answer there. So that longer wavelength, 740 nanometers, has less energy. That's the same idea we were sort of discussing here. So we have a range of energies from 1.68 electron volts to 2.96 electron volts. That range of values is going to be important for the next part here. It says use your data, or use data from one and your answer in one to show on figure 11.2 the changes in energy levels giving rise to the dark lines in A. Kind of putting all the ideas together. So we've got a range of photon energies where the least amount is 1.68. So for some reason, we only have this incident light of wavelengths from like purple to red or whatever. And that corresponds to these values right here. So just remember 1.68 and 2.96. photons from 1.68 to 2.96 electron volts. Now, the key idea that gives rise to the dark lines is that the difference in the energy levels, so these are the energy levels, right? Energy levels of the atoms in the cloud of gas. The difference has to be equal to the photon energy. In order for the electron to sort of see the photon, to interact with it, the energy has to be just right. So we might say, hey, can we promote anything up to this, energy level, but basically where it's sort of separate, ionized, separate from the atom. And if you take 13.6 and subtract any of these numbers from it, you'll realize there's just too much energy there. We don't have energetic enough photons. 13.6 minus 3.4, the gap here is 10.2 electron volts. Note that we don't have a photon with that much energy, okay? And it only gets worse from there. Like if you did 13.6 minus 1.5, it's like, could we promote from 1.5 to 13.6? Well, no, that would require 12.1, electron volts. And so those are not answers, right? Because we do not have that much energy. Conversely, like, could we go from this energy level to this energy level? So from 0.54 to 0.38 electron volts, that's 0.16 electron volts of energy. And note that all of our photons are too energetic. You might say, oh, we have enough energy, we can do that. No, we have to have just the right energy. So it's too low, actually. And so that's not a jump that we could do either. We can only promote electrons that correspond to those particular energy levels, right? And so we're looking for sort of difference calculations that lead to a difference that's within this range, right? So we'll take this, we'll jump these answers that are, are no good. And let's start to consider now, like from 1.5 to 3.4. 3.4 minus 1.5. Now that's 1.9. There's 1.9 electron volts of difference, and 1.9 is right in the middle here. So indeed, we could go from an electron that existed at this energy level could be promoted to this energy level. But then remember, it's going to be de-excited. It's going to jump back down, and it will emit photon of that same 1.9 electron volt energy, but in a different direction than our line of sight to Earth, and that's why it's scattered, and that's why there's a dark line. 3.4 minus 0.85. Okay, so there is an energy jump here of 2.55 electron volts. Now that's within this range, and so that's doable, that's possible. And so I'll draw that, like we could go from here to here, but again, it de-excites, it goes back down, and then emits a photon with 2.55 electron volts. That corresponds to a particular wavelength or frequency. If we keep working through, 3.4 minus 0.54, 2.86, and so that still is beneath 2.96, and so there's another jump we could do. But then you could start to sort of consider any other sort of gaps here, like, well, what about like between 1.5 and 0.85? Well, there's only 0.65 electron volts between these two. And so there's just, that's too low of energy, right? We need something that's at least 1.68, but less than 2.96. And so you could entertain every sort of jump that's on here, from this to that, from here to here, from here to here, and you'll find that those are the only three that work. So 1.5, like minus 0.38, that's 1.12 to get from here to here. Well, 1.12 is still below, right? So those are the three energy changes that could occur for the likely hydrogen, right? Like those happen to be the energy levels of a hydrogen atom. And so we jump from like the second to the fifth, or the third to the fifth, or the fourth to the fifth. But then go back down, and again, it sort of scatters the light, and that's why there's dark lines. And then we'd know, based on the presence of those dark lines, oh, this is a cloud of hydrogen gas, right? Because it's very particular specific wavelengths of light.